All right, dear colleagues, we are reaching this time. So maybe because Adriana told us to stick to the schedule, we should do that. It is a great pleasure to welcome you to this joint quantum seminar and the session of the Gamma Factory Physics Opportunities Workshop. We decided to do this joint venture in order for sort of these two partially overlapping sets to meet each other and to maybe expand the boundaries a little bit. And the speaker today is Andrey Surzhykov. Andrey is the director of a small institute for fundamental atomic physics associated with PTB. One of the enthusiasts of developing and summarizing the ideas of the physics program for the Gamma Factory, first in the atomic physics part and then now nuclear part as well. But the topic here is the atomic physics at the Gamma Factory overview. So welcome, Andrey.
Dima, many thanks. So you see my screen, right?
Yes.
Okay, so yeah, dear ladies and gentlemen, dear colleagues, so it's real my pleasure to give an overview of our dreams about what we can do at Gamma Factory in the realm of atomic physics. And I would like to say that this talk is based to quite a big extent on our recent paper, which was just published also in Annalen de Physique. And I would like, of course, to thank colleagues who contributed to this paper. So many of colleagues now, they are participants of this workshop. And also, I would like to say that the ideas which brought us to this paper and which are, let's say, basics for many ideas and many dreams which I will present here, they also came from idea exchange, from discussions with, again, many colleagues from atomic physics realm. So again, I would like to mention Julian, Stefan Fritsch, Robert from PTB, Adriana, definitely, Vladimir Shabaev, Valery Serbo. I would like to mention Jonas, Thomas Stolker, and Andrei Volodka, and also many other colleagues, especially from the Spark collaboration at GSI. So this is collaboration for atomic physics research with heavy ions at the storage rings. And I must say that some of ideas, they grew up after the joint and very nice work in the framework of the Spark collaboration. Yeah, I would like to start my talk with reminding the basic ideas of the Gamma Factory. So because as I understand and as it was agreed, my talk is actually talk not only at the workshop, but also at the Quantum Seminar. Therefore, for the colleagues who, for whatever reasons, missed the previous days of the workshop from the Mainz, I would like very briefly to remind the basic principles which we are talking here. We are talking about the rather simple idea. Do you see my mouse, please?
Yes.
Okay, the idea is very simple. So we want to operate with ions, with partially stripped ions, or how in atomic physics we would call it highly charged ions, stored in the storage ring of CERN. So in principle, our ultimate dream would be Large Hadron Collider. And the idea is that if we irradiate these ions with just a normal laser radiation, then due to the Lorentz transformation, the light which is emitted by the laser in the laboratory frame will be Lorentz boosted to quite high energies in the frame of the ions, which would allow, as it's shown here on the first very, let's say, artist view of the process, which will allow to excite quite highly energetically high length states of the ions. Then after some time, when ions will be in excited states, it will decay back to the ground state. And then the photon which will be emitted in the ion frame will be again boosted back to the laboratory system, and which after this two Lorentz transformation, which lead to the fact that from one laser photon, let's say, which is emitted just in optical visible region, we will get the gamma or even X-rays whose energy will be shifted up by 4 gamma squared, where the gamma is relativistic factor which describes the velocity of the ions in the ring. And again, I would like to remind you that at LHC ring, so the gamma factor could reach a few thousand. And I would like, so during the last 3 days already, today is Thursday actually, we had many discussions about what we can do with the secondary photons in the field of nuclear physics, in the field of the particle physics. We were dreaming how we can use the secondary photons when they collide with the targets to produce the further beams of particles and the photons. But I would like today in my talk mostly focus on the first step of this gamma factory operation, namely exactly to this process of the absorption of the photon, of the primary photon by fast moving ion, and the re-emission this photon after the radiative decay. So of course, even so, I would like to talk about overview, and I would like to discuss the various atomic processes. You will see, and from my discussion and from our discussion later, we have such enormous amount of processes which we have already in mind that I, to some extent, decided to restrict the analysis of the processes which can happen and which we can study exactly in this first step of absorption and emission. And I have chosen 4 case studies which easily can be extended to further discussions, further ideas. And basically, this is exactly our idea of this workshop, to initiate further discussions. And these studies will concern the spectroscopy of partially striped ions with, again, the primary photon beams. As the second idea, I would like to talk what we can revisit, rediscuss the ideas of atomic parity violations with partially stripped ions at the gamma factory. Then the third topic, which I would mention, it was we discussed already yesterday and we discussed on Monday, the idea of spin polarization of ionic beams by interaction with the laser by using the optical pumping scheme. And last but not the least, I would like really to consider this process of the photoemission, photoabsorption and photoemission as the process of the resonant photon scattering, which by itself is a very interesting point at atomic physics studies. But okay, let me start first with a brief discussion, brief review of the spectroscopical issues and how the gamma factory can help us at studying the spectroscopy of partially striped ions. In order to do this, I would like to say a few words, some general and well-known words for atomic physics community, and I would like, of course, to apologize to my atomic physics colleagues. So the next few slides I will say the things which you, of course, know very well, and I strongly believe some of you know them better than I do. But okay, as long as I'm giving overview, I would like to show the slides in order to be able later to address to wider community. And I would like to remind that we basically when we are talking about partially stripped ions. So these are systems from atomic viewpoint. From the point of view of electronic structures, they are very interesting and very complex systems. Because I was also impressed of this, the cover of the CERN journal when the information was about the first ion stored at LHC. It was written something like first atoms at the Large Hadron Collider ring. But to say atoms, it's too rough saying. So actually the world of atomic physics and world of partially stripped ions is much more interesting and much more colorful and vivid as just saying simply atoms. And here I would like to remind you that, of course, yes, we can start from the many electron heavy atom, let's, for example, lead atom, and then to remove all ions, all electrons from it. In this case, we can produce what we in atomic physics we would call bare ions. In nuclear physics, you would simply say this is just a nucleus. We can leave one electron. In this case, it would be hydrogen-like system. We can leave two electrons. It will be helium-like system, 3 lithium, and so on. And again, I would like here to stress that usually we in our community call these guys as a highly charged ions, but in my talk, I will use the terminology of LHC, of the CERN community. I will call them as a partially stripped ions. So these partially stripped ions in different charge states, basically in the focus of long-going and very intense research. And nowadays we have two branches of this research. One branch is we can produce, store, and operate with each ions in the large accelerator and storage ring facilities, like, for example, here it's already existing GSI facility in Darmstadt and the facility under construction, which is FAIR, Facility for Antiproton and Ion Research. The second branch, we can produce these ions, maybe not in a very high charge states, or depends on the nuclear charge, in the traps, and for example, electron beam ion traps, and then to operate with ions, for example, by shining laser on them. Why it's so important? Why it's so interesting to talk about these ions and about the spectroscopy of these ions? First of all, from the atomic viewpoint, there's a very interesting system which allow to study the simple atomic systems in the quite extreme regime. So very simple arguments. First of all, if we're talking about system of just few electrons coupled to the heavy nucleus, the electron stays very close to the nucleus and nucleus is very big. We having a situation when electrons spend most or partially their life inside of the nucleus. Therefore, the nuclear effects becomes important. The electrons move very fast around the nucleus, and so this is a simple estimate from the simple Bohr theory, which tells us that the velocity of electrons in the orbit of the ground state of hydrogen-like system, it's alpha z times speed of light. So that means that for uranium, for example, electrons on the orbit move with 70% of speed of light. The electrons exist in these ions in the very strong electromagnetic fields. For example, here I displayed the electron density. So here's the blue curve, and the red curve is the electric field strength as produced by the nucleus, depending on the distance from the center to the nucleus. And we see that half of the electron wave functions actually exist even in the felt strengths, which is higher than so-called that's the limit for the at which basically vacuum might become unstable, and in principle, if we would have good conditions, we might observe the electron positron pair creations, but of course not for such strongly strongly dependent fields. So sorry, I'm a little bit lost my trace here. Yeah, and so this is very important that these ions, they are can be considered, and they considered, for example, at studies at the GSI, at FAIR, as the natural laboratories for studying atomic systems under critical conditions. What is very important to understand when we are talking about these ions, that the energies, the typical energies of these ions is absolutely different from those which we usually get used in usual atomic physics, in physics of usual atoms. For example, the fine structure splitting between the levels is on the level of the kiloelectron volts. Even hyperfine structure splitting is at the level of electron volts, and the QED effects, the shift, for example, the lamp shift of the energy levels might reach tens or even hundreds electron volts. And the binding energy itself is the KeV regime. That's basically why, if we're asking why we need gamma factory, because the answer is partially hidden in this table. Yes, with gamma factory, we can reach the high energies, maybe not extremely high, like 100 keV, but at least the level of the fine structure, hyperfine structure, and QED transitions. In order to illustrate this idea, here I showed the calculations, just a back of envelope calculations for the transition energies for the hydrogen-like ions between the ground state and 2 p3½ state. It's one of the two states of the fine structure of 2p level, and lithium-like ions, which is of course of interest, especially in the sense of proof of principle experiment. This splitting between the ground state 2s and the first two excited states 2p1½ and 2p3². The calculations done again. Here we have energy, and here the so energy of these transitions for the different nuclear charges. And with the blue background, I have indicated, so assuming the maximum gamma factor which we can reach at the gamma factory, so 2900, we can reach this energy region, which is marked here with a blue color. So that means in particular that with the gamma factory, we can consider the excitation from the ground state of lithium-like ions to the excited states, for example, p1½ and p3½ as the first and second excited states, as it's shown here, for basically any ions which we can produce and which we can operate nowadays at the storage. For example, here, lead ions stays here. And
Andrey, sorry, quick comment. That's probably assuming something like 1 electron volt of the initial laser.
2 electron volt, I assumed here.
Well, it's the factor is 2 gamma, so it's 6,000. So if you start with 10 electron volt, which is in principle possible, then you get up to 60 kilovolts. I mean, it's a difficult laser and whatnot, but I think one can.
Okay, I understand what you mean. So okay, I agree that I was too conservative here, and by using, let's say, UV lasers or even more advanced laser, we can go even high here. I agree, Dima, with you. So I was, let's say, I decided to be, and you will see also in the later slides, I decided to be a little bit more on conservative side. But I agree with you. So this is not a limit. So we basically, this is very conservative limit. We can go even higher. But for lithium-like ions, even for this conservative estimate, we can really cover all any basically transition between the ground state and the at least first excited states, and even to going to the 3p states also easily we can reach with these energies. And this is of course the first step on the gamma factory. This is the first proof of principle experiment. Of course, I mean, from the viewpoint of gamma factory, this experiment is just idea. We exciting the ground state to the first excited state, then we decay and we produce this secondary photons. This is good. But we, as atomic physicists, would like to see on this experiment as a spectroscopy experiment. Because lithium-like ions, so this is, again, my artistry of lithium-like ions, the ion with the 3 electrons, and the ground state and the first 2 excited states of such system. These are basically one of the very fantastic, very convenient tools to study the simple atomic system. So they are from one side already quite complicated. They have 3 electrons. That means we can address questions about analysis of the electron-electron interactions. From the other side, they are quite relativistic and strongly bound system to study many nuclear effects, to study QED effects. And just to give you a feeling, what does it mean from the theoretical point of view to estimate to good accuracy the energy levels of this lithium-like system, I presented this table from the rather old paper, theoretical paper by Vladimir Yerokhin and Vladimir Shabayev and Pauline Delicata. So this is not the latest calculations, but that was a paper in which this table was presented, which I find it's very good from the didactic viewpoint. So you can see how many contributions, starting from just taking into account the final nuclear size, taking into account effects of electron-electron interactions, nuclear polarization, recoil effects, various quantum electrodynamics effects, you need to take into account in order to get agreement with experiments. So here, for example, is exactly calculations and experiments, calculations for 2s, 2p1½ transition, exactly our transition, but this results is not for leads, or namely for uranium ion. What is important to understand that on experimental viewpoint, for the moment, the most accurate measurement of the 2s to p1/2 transition is exactly this experiment by Peter Beisdorfer. It was experiment with EBIT, with Lawrence Livermore National Laboratory EBIT, where they measured the energy of this transition with accuracy of, you see, 0.015 electron volts. And this is already accuracy, which allows from theoretical viewpoint, address very important question of this line of the two-loop QED corrections, which nowadays, and in particular with regard to this discussion of the proton radius and all these issues, they're very important point from the theory, from the quantum electrodynamics. I shouldn't say too much here because this is basically, I hope, and I think it will be in talk of Vladimir Shabayev just very soon, today also. And Vladimir is definitely expert in these QED calculations. And of course, I think he will explain this and he will discuss it better than I will do. I will just, to finish this spectroscopy issue, I would like just to show the table of the most precise calculations up to now for our transition, for transition of interest for the gamma factory, for the 2s to p1/2 transition in lead ion. And so you see here, we have a number of calculations starting from rather old Sapperstein calculations and going back to the, again, calculations done by a St. Petersburg group and by Vladimir Yerohim. So this is the theoretical calculation. This is the theoretical uncertainty of these calculations. And from the experimental viewpoint, I would like to stress that to our knowledge, the proof of principle gamma factory experiment will be the first observation of 2s to p1/2 transition in lead lithium-like ion. So for uranium, there have been experiments by Peter Beisdorfer. For lead, it will be the first experiment. And moreover, we expect the accuracy. So based on the parameters of the proof of principle experiment, the accuracy is very high, higher than it was in previous experiments. And the accuracy, which is even higher than accuracy of the theory, which again will allow us to address important contributions to these energies, in particular this two-loop QED corrections. But again, I should now say no word here because definitely Vladimir will explain and will discuss it much better than I. Let me come to the next important point is this parity violation studies. This again, just one slide to remind what we are talking about. When we are talking about electron or electrons coupled to the nucleus, then due to the fact that in the standard model, the electroweak interaction is a joint, it's an interaction which combines the exchange of not only gamma quant, but also of the gauge bosons, we can have the additional to our interaction between electron and the nucleus due to the exchange of the Z boson between electron and the nucleus, or due to the exchange or normal electromagnetic interaction of electron with the nucleus, but with the nucleus in which processes of the exchange of the V or Z bosons takes place. So these two parts usually referred to as nuclear spin independent, and this is the main part of the interaction, which is again, I mean, in the artistic way described by this Feynman diagram, and the spin dependent interaction, which is this diagram is responsible. Not only this, there is some other processes which also gives rise to this nuclear spin dependent part. But for us, it's important to understand that yes, we have these additional terms in our interactions, and they lead to very important effect that the atomic levels which having the opposite parity, for example, here, just for simplicity, I displayed the atomic levels. So this is, I even don't specify what the atom is here, but the levels of S and P, which usually have a parity plus or minus, they can be mixed due to this effect of the weak interaction. And as it goes from the perturbation theory, we can show that this mixing as larger, as closer levels laying to each other, because in this mixing coefficients, which allows us to calculate the mixing between these two states, is inversely proportional to the energy splitting between these two levels. And we know that the last decades, a number of parity violation experiments have been done with neutral atoms, or at least with ions, but not in the very highly charged states. During the last decades also, the idea came that the partially stripped ions, that highly charged ions, could be a good candidates for parity violation studies, as they can offer a good alternative to experiments with, for example, neutral cesium. Why this? First of all, highly charged or partially stripped ions, they having relatively simple atomic structure, and this is really important for the analysis of the parity violation experiments. Second, as I said already, these ions have a large electron nucleus overlap. That means that the effect of the weak interaction might be enhanced. And really, we see this if we are analyzing the scaling, the z-scaling of the matrix element for the parity violation, which scales a z to 5 for highly charged ions in contrast to z to 3, if I'm not mistaken, for the neutral atoms. And second, or the last but not the least, that the partially stripped ions with all this variety of charge states, they allow us to find the system which have levels of the opposite parity which are almost degenerate. Very good example for this is a helium-like ion. So the system of two electrons in which the singly excited states, so 1s, 2s, and 1s, 2p, can be almost degenerate depending on the nuclear charge of the system. For example, for the equal 62, it's around europium, and 92 around uranium. The levels of the singlet S0 and triplet P0 can be degenerate, which makes the system as very, very promising candidate for the studies of the parity violation. And during the last years, during the last decades, a large number of proposals have been done how to measure, how to observe the mixing between the levels. I will not go too much into the details. I would like to simply say that in all these proposals, the main idea was the following. The idea was to produce our helium-like ions in excited state, mostly in this 1s to s singlet S0 state, and then to induce transition from these states either to some low-lying level. It was, I think, originally idea discussed by Vladimir Shabayev and his group in 2010, and to induce transition, for example, to triplet S1 state, which would be M1 transition plus, due to the parity mixing, parity violating electric dipole transition, and then by inducing this transition with this left and right circular polarized light, we can observe the asymmetry in the cross section and the rates, and from this asymmetry to get information about mixing between these levels. Another idea was originally initiated many years ago. It was also work of Andreas Schäfer, Pauline Delicata. I think Gerhard Zoff was also co-author here, to induce the two photon transition from between the singlet S0 and triplet P0 state, which is 0 to 0 transition, which means this two photon process. But if we really choose the proper polarization of the photons, we can induce this transition only and solely via the parity violating 1-1 transition. There are many others proposals, so there is really a big portion of the proposals how to study the parity violating mixing in highly charged ions. The problem in all these proposals, as you see here already from these examples, that they all start from the excited state of the ion. And this is a problem. For heavy ions, these excited states has a very short lifetime. Therefore, we need always compete with the spontaneous decay of this excited state. And in order to compete this, we need to bring more and more higher and higher laser intensity. And this, of course, disturbed our system, and this leads to problems for the implementation of the schemes. Even so, some of the schemes now, again, they are discussed for the implementation with all the corrections in the framework of the GSI experiments and the Spark collaboration. The
Andrey,
gamma
I
factory.
really hate to tell you, but you just have maybe 3 minutes left.
Okay, thank you, Dima. For gamma factory, the great advantage that we can excite our system from the ground state. We don't need to compete with the spontaneous decay. We just can consider the excitation from the ground state to, for example, 2s state mixed with the 2p state in hydrogen-like ion, in helium-like ion, even in beryllium-like ions. In all this system, we start with a state which is either ground or at least metastable, like triplet P0 in the beryllium-like ions. And then we again apply left and right circular polarized light and look for the asymmetry of the transition. And so here I just did, or not me, so the student of my, so Jan Richter, who just sits next door to me, he did a back of envelope calculations for this simple idea of the 1s to s transition in hydrogen-like ions. And for example, based on this calculation, so he calculated the parity mixing parameters between 2s and 2p1/2 state, which looks like this. So you need to multiply these numbers by 10 to minus 8 to see this mixing parameter. And then if you make these experiments with the left and right circular polarized light, if you will get this asymmetry ratio in the Z domain, which, let's say, not very high Z, but relatively high Z. So this can be approximately 10 to minus 6. So this is just to give you impression about the size of the effect for these systems. Another, of course, very important issue, which is the next step in the studies, it's the search for the permanent ADM, electric dipole moment, either for nuclei or for the electron bound to the nuclei. And here, again, the idea of implementation of highly charged ions or partially stripped ions have been worked out by Josef Hriplovich and also by Leontiy Labzovsky and his group in St. Petersburg. And in this idea, in this experiment, there is different schemes again, so I don't have time absolutely to go into details, but the idea is to observe the precession of the nuclear spin or of electron spin of ion spin in the combination of electric and magnetic fields. But the problem for all these scenarios is they require to have a polarized ions. And this is exactly the discussion which we had yesterday and on Monday, that we would like in the gamma factory to think about polarization of ions. Polarization of ions means for us both polarization of the electron cloud and polarization of the nucleus. And yes, we can do this if we will consider the optical pumping of hyperfine levels of the system with when nucleus has non-zero nuclear spin. This was one of the ideas which was again proposed by Leontiy Labzovsky and his co-workers in 2003. I think also many GSI colleagues were co-authors of this paper. The idea, they did a simple calculations for the case of europium-62 plus, so it's hydrogen-like europium ion. And they just said, okay, if we put B field along our light, and if we will induce the transition between the ground hyperfine level and excited hyperfine level with the circularly polarized light, then due to the fact that at each absorption of the light, our population will be shifted by 1 unit of projection, for example, in the direction of the higher projections, then sooner or later, we will create the dark state in the hyperfine sublevels, which would have almost 100% population of the substates. And of course, for this discussion, it's a very important question. So Dima, 2 minutes, yeah? And for this discussion, very important question is not only producing of these ions. So the producing, at least we see that, yes, if optical pumping works, it will produce the predominant population of some or this hyperfine level, depending of which helicity, which circular polarization we apply. But the issue is that whether we can preserve this polarization in ion storage rings. And we had discussion yesterday about the application of Siberian snakes, which allows to compensate effects of the bending magnet in the ring. But recently, we analyzed and we discussed experiment which was performed at the GSI storage ring, in which the optical pumping of helium-like lithium ions have been observed. So lithium plus, it's a system with 2 electrons. And in this experiment, the pumping, a little bit more complicated scheme, it was this lambda transition. So it was 2 ground levels. No, ground, they are in the metastable state, but this state lives almost forever, and 1 excited state. And by applying 2 lasers from 2 directions, it was possible to consider the lambda transition between these 2 levels. And from the analysis of the polarization of these lasers, which induces lambda transition, it was found that if the circular polarization, if the particular combination of circular polarization of this laser is applied, we observe the experimental results. Again, I don't go too much into details, which might be seen as the indication of the optical pumping of hyperfine levels, and what is more important, of the preservation of this polarization in the bending fields, in the bending magnets. The last few words about the resonant photon scattering. As I said, the first step in the gamma factory operation, it's really process of the photo absorption and photo emission of the photon. So again, I mean, up to now, we're considering this process as really a tool to produce the secondary photons, which we'll want to use later for whatever studies. But basically, the process by itself is also of interest for atomic physics. Because in principle, the scattering process, the process of scattering of X-rays by partially striped ions during the last years attract really considerable attention, both in theory and experiment. In theory, the analysis of this process is very interesting because it allows us to study the different components of this process, which is not only scattering on the electron cloud of the electron, which is usually referred to as Rayleigh scattering, and which is, of course, the main contribution at the energies which we are talking about, 100 kiloelectron volts or below. But if we go to the higher energies, we can even consider the process of the Delbruck scattering, which would contribute also to this process. And from the experimental viewpoint, we also have very interesting studies during the last years where this process of the photon scattering was studied both in the non-resonance regime at Petra 3 in DAISY. So that was experiments by Thomas Stolker and his group in framework of SPARC, and resonance scattering. So this is exactly our process on the partially striped ions at the EBIT facility. That was experiment by where Jose Crespa and myself, we took part in the analysis, where the X-rays were produced by the synchrotron radiation by BASI 2, if I'm not mistaken, in this experiment. And for this resonance scattering, of course, it's very interesting and very important. So really to understand the characteristics, the properties of this scattering process. So here I just show the Feynman diagram for the scattering process as we see as theoreticians. And here I show the cross-section of this process for the different photon energies. So here just test calculations. So here is elastic X-ray scattering by hydrogen-like lead ions. So okay, I was a little bit stupid not to make calculations for lithium-like, but when I already ran these calculations, I said, okay, let's be hydrogen-like. So we see that this is really when our photon energies really fit into the transition energy, into the splitting between the, for example, 1s and 2p state and 1s, 2p, 3 half state, we really observe these resonances. And so this is exactly our process of the resonance scattering. But okay, cross sections is interesting. It's important to know in order to plan experiments. But we are very much interested in the question of the angular and polarization of the scattered photons. And in the non-relativistic regime, the answer is very simple. So here's the answer to all questions about polarization, about the angular distribution of scattered photons, about everything. So here's the answer. But the life is much more complicated. And in relativistic calculations, so we can show that the, for example, amplitude for the photon scattering excitation and de-excitation of our ion is only partially contributed this term of the product of the polarization of incoming and outgoing photons, which would give this non-relativistic regime. But in relativistic regime, we have some additional terms which comes from the tensor product of the polarization vectors, and which leads to much more interesting, much more colorful and various contributions to the angular polarization properties of scattered photons. So again, I think that Andrey Volodka in his talk will discuss this in more details. And the last but not least, of course, when we are talking about the polarization transfer, we can also talk about the transfer of the orbital angular momentum. And this would require from us to discuss the issue of the scattering of the twisted photons. Again, I would like simply to say that Valery Serbo, who will give a talk after me, he will address this question. Yeah, so this is a summary. And I, by purpose, focused only on the first step in the gamma factory operation, only on the process of the absorption of the photon and re-emission of the photon. So, of course, these 4 case studies, which I was trying to briefly discuss, they're only just a small portion of the studies which we were already dreaming and which we wrote in our Annalen der Physik paper. So more ideas can be found here. And we hope, of course, that even more ideas, probably even more interesting, probably even more attractive ideas will be proposed by you and by our discussions. So you're very welcome to contribute to this. And thank you very much for your attention.
Thank you so much, Andrey, for this wonderful talk. Very good overview. The talk is now open for questions.
So I have a question.
Yes, Mariana.
For the spectroscopy studies, do you need to cool the beam in order to reach theoretical uncertainties?
Yeah, so when I said that we have a good let's say, good expectations about accuracy, we assume the relative spread of the in the momentum as a 10 to minus 4. If I'm not mistaken, this is exactly what we indicated in our this review paper. So we assumed that, okay, 10 to minus 4 is a relative spread of the longitudinal momentum.
Mm-hmm. And the second question, all of the parity violation, especially DM studies, the main issue was always systematic effects. Is there some assessment of what those would be to actually, is it feasible to actually have those under control in those very difficult experimental conditions?
This is a good question. Of course, this very much depends on a particular scenario, right? For example, if we are going back to this original proposals, for example, by Hriplovich, yeah, he was, for example, proposing to, or by Lapsovsky, better to say. So he was really proposing to producing the polarized ions and then sending them in this combination, in the proper combination, electric and magnetic fields, and searching for the spin precession. So, of course, in this case, he's extremely sensitive to the field configuration and to all the non-homogeneities of the fields. And this is, of course, a big problem for the moment, completely, for me at least, terra incognita for the gamma factory, because of course it's clear that our ions in their projectile frame will see the Lorentz transformed fields of the ring, but how they will transform, what will be the configurations of this field, for the moment, I unfortunately, so this is a topic still need to be discussed. And of course, it depends very much on a particular configuration. And for example, as I already understand, I'm theoretician, so I'm not experimentalist, but as I understand, for example, the condition of the SPS experiment and of the LHC experiment will be already different. So we would need really to address each particular experiment, each particular configuration. So fairly speaking, this is still topic which is completely, completely terra incognita for us.
Vitik, you would like to add to this?
Only to correct a little bit what Andrey answered to the question of Marianna. As a matter of fact, you should understand that the highest possible precision that we have at the moment on the absolute calibration of the momentum of particles which are stored at the SPS is at the level of 2 × 10⁻⁴. So this was obtained by comparing the velocity of in the SPS of the ions of lead with respect to protons, and we cannot beat this. If you think about the precision which goes to 10⁻⁵, then you should configure your thinking in atomic physics in the following way. You put, for example, calcium atoms or something that has low Z, and then you measure it as a calibration of the absolute scale of the energy. And then you go, for example, to lead, to lithium like lead, or some other configuration, and it's only in comparison of 2 atoms that you can go to better precision. So my correction is, it is not the question of the spread of the momentum which we can adjust by cooling, but the question of the knowledge of absolute momentum of our particles in the SPS, which is at the level of 2 × 10⁻⁴. So please think of the schemes in which you chase, for example, the weak effects and the vacuum effects, in which you run the pairs of nuclei, and the first is to calibrate, and the second is to measure some contribution which is of new type.
Why is calcium better than protons? Maybe a very naive question. You mentioned calcium ions?
Vitik?
Or barrier nuclei?
Vitik?
I kind of missed the whole calibration. How would it actually, why would it make a difference?
So, Vitik, are you there? Okay, something happened.
Sorry. Let me just put it in a straight way. The highest precision in the configuration, if you would run protons and lead ions, of the absolute precision of calibration of your transitions, you see, energy, is 2 × 10⁻⁴. If you would like to look for the effects which are specific only for high Z ions, then the only possibility of going to better precision is to compare the calibration that you would get by running, for example, calcium, which is probably the ion that has if you go to lower Z, the lifetime of the beam is too short in the SPS. So we should probably start with calcium. And then you measure the transition energy with calcium, whatever you like. And then you use this value as calibrating the transition energy for example, lead, for lithium-like lead. And for the relative measurement, you can go to precision of the order of 10⁻⁵, or maybe even better. But do not think that we would give you the absolute scale of the energies of the transition based on our best knowledge of the absolute calibration of particles which are circulating in the SPS.
Although in the paper we have also a discussion of an idea of measuring energy of the secondary photons very precisely, and that sort of calibrates the whole measurement.
Yeah. But you see, the best precision that was obtained with by measuring the N spectrum of the photons is of the order of 5 to 6 10⁻⁵. So if you would like to go still further, so you see, I was telling you what will be the scheme in which you could go further in precision in terms of measuring the energy levels. From the N spectrum up to now, there was no measurement that was better than 5 × 10⁻⁵.
But nevertheless, I would like to stress again that my statement that even at the accuracy 10⁻⁴, we can already make a good spectroscopy. And this is already then we can further discuss whether we want to improve it, whether we don't want to improve it. But already at this accuracy, we can do a good spectroscopy on the level comparable with, if everything works well, with the Peter's experiment with the EPIT.
And this could always challenge the, you see, the understanding, you see.
Also, to Mariana's questions about EDM, the EDM schemes have not been analyzed in any detail for the gamma factory scenarios, because we sort of need to understand whether polarization survives the round trip or not. However, as already mentioned in this workshop, there is another study group as part of Physics Beyond Colliders that is specifically dedicated to EDM measurements and storage rings, and they have very, very good understanding of the issues there. So I think this analysis can be carried out once we know that the polarization survives.
Thank you so much, all. It's fantastic.
Any other?
No, but I mean, Mariana, we should also understand that for the moment, I mean, we have, I would like to stress that even in these slides, in these studies which I discussed, we have some better and some worse developed ideas. Yeah. So for the moment, we are still in the stage of collecting ideas. So it might happen absolutely easy and absolutely without problem if you come and say, no, with EDM, it wouldn't work. Okay, then we say, yes, okay, that's life. Yeah. So no, but I really would like to stress that, I mean, we are on the stage of collecting ideas.
Andrey,
Thomas?
may I make a comment? Andrey, it's Thomas.
Thomas, nice to hear you.
It was really a great talk. And I like in particular the discussion about the polarization of the ion beams, of course, as you know, old dream. And but nevertheless, in case of EDM, I think we need to be careful. You know, all the EDM proposals which have been made, in particular now, I think Jülich is here, put a lot of efforts in, but at the end of the day, you need everywhere an electrostatic storage ring, because you need this enormous accuracy and precision.
Of the control of the
and I think just now such kind of an electrostatic storage ring is under discussion for CERN, and it was also proposed actually, I think, by Jungmann and al. From KVI for FAIR, but they want to do EDM with an electrostatic storage ring using exotic nuclei, where the EDM effect is again amplified by orders of magnitude. Okay, only as a general comment.
Thomas, thank you. In principle, this is exactly what this is very good comment. Yeah, because of course, I mean, even in these older proposals by Hryplovich and by Labzovsky, of course, they rely on this on the static electric fields, yeah, and on the proper equipment. In our case, situation will be much more difficult, because we will see it, as I said, in the moving frame, and configuration of the fields will be very complicated. Yeah.
And maybe also a final comment about spectroscopy. I think there are really unique physics opportunities in terms of spectroscopy at Gamma Factory. But I think it's really of utmost importance to find out what accuracy I finally can expect, in particular also with regard to other facilities where similar experiments are currently planned and will be performed. So I think precision is the key. And for relativistic ion beams, of course, the control of velocity and the gamma factor is the key. It's completely clear.
Yeah. Totally agree, right? Yeah.
Thanks. Thanks. Any more questions? Because we gotta also be moving along with our program, but maybe one last short question.
I'm just trying to, I mean, like a super technical and boring question to everybody, and you know it by heart. How many ions are in a bunch that you interact with? And I mean, just trying to figure out how many photons it scatters per round trip or per illumination with a laser beam.
I think Vitek, you're the best.
So for the lead, for example, if you would run a lithium like lead, you may expect almost 10 to the 8 ions per bunch, and you can have, I don't know, of the order of 20 bunches in the SPS. If you go to calcium, then you basically can keep of the order of 3 times 10 to the 9 calcium ions per bunch with the same frequency. At the LHC, you basically go to 1,000 or between 500 and 1,000 bunches of this size. And you see a reminder, in the gamma factory, we are thinking of exciting in one collision point an ion which has the decay length of the order of a fraction of millimeter, not once, but probably 3 or up to 10 times.
Thanks.
Okay, cool. So thank you for the discussion. I just would like to cordially invite the quantum people to stay on, because I don't think you want to miss the next talk by Professor Surzhykov. What do you guys please share your slides and let's go.
Maybe I can also, just for the quantum people and for, of course, the Gamma Factory people, make a little advertisement for next week's seminar that we have here in Mainz. And that will be by Lars von der Wense from GILA about the 229 thorium isomer and new clock, so a nuclear clock using this. Next week, maybe I post our Zoom link in the chat here, so that you can all join if you want.
Maybe send it to Oli, but perhaps then we can also display it on the somewhere.
Cool.
Yeah.
So thanks for hosting us.
Yeah, but please stay, because okay, please.